So finally, we're going to have now our 10th lecture, and the topic is going to be an application of the formalism that we have seen for open quantum systems to spontaneous emission. So we're going to go slowly, we're going to do this in the whiteboard, but this is because this is very important so that you can understand how powerful this is and you will get a grasp of how this whole thing works. Okay, so let's do it then. Hang in there, see you soon. Okay, so we're going to set up the problem and we're going to discuss how we apply the Lindblad formulation of the Markovian evolution that we have just derived for a problem which is very well known, which is spontaneous emission. And what we're going to consider is we are going to consider a two-level atom. So it's going to have, let me draw this better. We're going to have an excited state E, a ground state G, and this, as we have seen in previous lectures, is quite useful for describing the physics of systems which are more complicated, but which have a pair of levels which are strongly coupled. So here, just to specify, G is our ground state. E is our excited state. The energy in the ground state we're going to set to 0 for simplicity, and the energy in the excited state we're going to set to be h bar omega. So these two states, they're separated by h bar omega. And this allows us to write the Hamiltonian. So the Hamiltonian of the system is given by this expression, h bar omega E E. And the problem that we would like to address is the following. We would like to look at spontaneous emission. So we have an atom, for instance, interacting with an empty field mode, and this atom is going to emit a photon. In a cavity, it could interact with a single photon many times because it would be trapped. So we wouldn't have an evolution that we can treat as Markovian. But in the free space, it is very unlikely that the photons are going to be reabsorbed. So we're going to focus on free space. And this means then, if this is unlikely, we can consider the evolution to be Markovian. And we can use the Lindblad form master equation, which we have previously seen. So we are going then to write this equation for this specific system. And this is going to be a nice example of how this interacts with the environment. We could do it more rigorously, so we could derive this evolution from first principles, solving the time-dependent Schrödinger equation for a two-level atom in a field, and then tracing out the state of the field. If you are interested, do have a look at quantum optics books. That's not how we're going to do. We are going to start from the formulation that we have derived, which is to a certain extent phenomenological, but it is quite powerful, and this is going to illustrate how we can go about it. So let me make a note that we could have a rigorous procedure. Which would mean to solve the time-dependent Schrödinger equation for the whole system. Then you trace out the state of the field under a series of approximations. And this is something, if you are curious, you can check in quantum optics books. I'm not going to do this here. It's quite involved. That is the right way of doing it. But we're going to see how we can do this using the formalism that we have just learned. So this would be also Wigner, Weisskopf theory. So we would like to write this Hamiltonian, this effective Hamiltonian. So let's consider our situation. Our Hamiltonian is given by h bar omega, then this projection to the excited state. We have conveniently chosen the ground state energy to be 0. And we're going to define a jump operator. L is going to be just one, no complicated sums. Gamma, and then you have this GE, this operator here. So one thing that we can see is that we embody spontaneous decay. So this is a rate at which spontaneous decay occurs. And this is also going to transform by applying this, the excited state to the ground state. So transforms the excited state to the ground state. Okay, so because we have a Hamiltonian, we have a jump operator, we can define an effective Hamiltonian. So let's have a look. And H effective in our case is going to be H minus I, H bar divided by 2, sum from J from 1 to infinity, Lj dagger Lj. However, we just have one term here, which is the one we're going to calculate by using this. So calculating L dagger L is going to give you gamma star EG, which is L dagger, applied to gamma GE. And from here you see that you will get modulo square gamma E G G E. Here we use the orthonormality of this basis, so we know that this is equal to 1. And therefore we can say that L dagger L is given by modulo square gamma EE. And our effective Hamiltonian is thus given by H bar omega minus I H bar 2 gamma square EE. Now there's a few interesting things I would like to pay attention to. First, if I write this like H bar, this is going to be omega minus I gamma square divided by 2 EE. This is as if your Hamiltonian now had acquired a complex energy, because this is pretty much of the form, if you wish, where you have E effective applied to this guy, which is a projector onto the excited state. So we can say also that in this case we have a non-Hermitian Hamiltonian, but it's not pseudo-Hermitian because you can clearly see that the eigenvalues are not real. You have a complex eigenvalue, and this is associated with decay. So you have VH effective is non-Hermitian, and H effective has an effective complex eigenvalue, which is given by EF H bar omega minus I H bar 2 gamma square 2. And this can be associated with a width, if you think about it, and that's pretty much the picture you use in decay. If you have eigenvalues of the Hamiltonian, which are real energies, you have just something like this. But when you have a complex part, what you do is you put like a width in the excited state. So you are pretty much introducing decay in your framework, which is something that you aimed at because you're considering the interaction with an environment. And remember when we mentioned this in one of our first lectures. So this is just a brief statement, which I will look at later on, and is not the main topic of the present lecture. And what we are going to do now is we are going to look at the master equation because we are interested in the evolution of this system. And we have the effective Hamiltonian, we have L, we have everything. So we just have to compute dot T is equal to the super operator, which is going to be H effective T minus rho T H effective dagger plus L rho T L dagger. And we're going to assume that our system is initially in the excited state. We want it to decay, so we're going to put it initially in an excited state, or because we have a two-level atom, we just have one. So rho 0 is given by E is this projector. So one thing that is very important for us to do is to write the density matrix of the system. So let's do that. And we're then going to have the state psi t, which we can compute by considering a closure relation onto the basis. So we can write this inserting, let me put it explicitly, E plus G, which is the identity operator, psi t, and so continuing, we can write this then as E psi t E plus G psi t G, where these guys here are integrals, which are going to be complex numbers. Not going to go into detail, this is something that we have already seen, but we want now, let's call this CE, let's call this CGT. We'll carry this along. And now what we will do is we're going to calculate this, which is our density operator in the compound system. It's pure, but it's not pure in the subsystems. And we're going then to have that this is going to be CETE plus CGT G applied to CE star T, which is just what you would have for the dual vectors and in the dual space. So you take the conjugate of the overlap integrals and you take the corresponding brass. Okay, so if we expand, this is going to give me CE star T, CET, E plus CET, CJ star T, GE plus CE star T, CGT. It's the other way around. Hang on. Yeah, sorry. So here is the star because I'm taking the bra. And the star is going to be here. Okay, deal. Plus CG star T, CGT, GG. Now, I'm not going to show this, but if you, by chance, consider that your initial state is the excited state, which is something we have done, you can show that the cross terms are going to disappear. But what I'm going to do is I'm going to write this as Ho EE, as Ho EG, this as Ho GE, and this as Ho GG. Because after all, what we're doing is we're writing the density matrix in these two-level basis. So this is a fair enough point. So this is Ho EE TEE plus Ho EE GEG plus Ho EGT GE plus Ho GGT GG. Not so nice. Okay. Now, simplification. I'm not going to do this, but you're welcome to try this at home. Namely, if the initial state is like this, a projector onto the excited state, then Ho EGT is going to be equal to Ho GET, which is going to be equal to 0. Both terms are going to vanish. We're going to consider this. If you are in doubt, you can prove it. I'm not going to do it, but this vanishes for all times. And this means that this whole expression that we have here above is going to simplify and is going to become Ho EET EE plus Ho GGT GG. And we want to describe, we know that these are probabilities because of the definition of a density matrix, and in this basis it's a mixed state. And we're going to insert this into the Lindblad equation. So let me state that, because after all, we want to compute the evolution. But before that, we want to do the following. We want to see how L and H effective are going to act onto the ground and excited state. Okay, so let's first check how L and the effective Hamiltonian act on the excited state and on the ground state. Fair enough. Let's have a look. So we apply H effective E. You're going to have H omega minus I H bar divided by 2 modulus gamma square E, which is this projector. And then here you have E. So this is equal to 1 because the basis is orthonormal. So you basically find that this is H bar omega minus I H bar divided by 2 modulus gamma square excited state. Okay, now let's have a look at this applied to G. So you have HF applied to G. This is going to be H bar omega minus I H bar 2 gamma square EE, so it's a projection onto the excited state. Because excited and ground state are orthonormal, I do expect that this is going to vanish. So we know that H effective applied to G is going to vanish, is going to be 0. And the Lindblad or the jump operator applied to the excited state is going to be gamma G E E. So this is equal to 1. And from here we can see that this is going to give me then gamma G. So as expected and as stated, this made the system jump from E to G. I mean, after all, it's a jump operator, and you can see as well that if you apply L to G, you get gamma G E G, and this is 0 because the states are orthonormal, so you get 0. So we know how they work, and now we're going to compute H effective gamma T, and then take the dagger from that. So let's have a look, because this is the first part of our Lindblad equation. Okay, so H effective gamma T is H bar omega minus I H bar 2 square modulo square gamma E E applied to gamma or whole EET, then this projector here, plus whole GG, GG. We have seen already that if you apply this guy to G, is going to vanish. So we know what is going to happen, but just to be thorough, let's do this again. So we're going to have then that this is going to be H bar omega minus I H bar gamma modulo square 2. I'll leave this outside. Ho E E E E E E. So this is equal to 1. And this gives me then E E, which doesn't surprise me because after all, this is a projector. This is a projector. We have seen that P2 equal P if you have a projector. So that's actually what you expect. Plus Ho GGT. Then you have this projection to the excited state, but you have this other state which is orthogonal, so this is 0. Done. So we know that H effective Ho T is given by H bar omega minus I H bar divided by 2 gamma square Ho EET, and then this projector onto the excited state. Okay, now it's easy to calculate the adjoint, because we need then, if you want to calculate Ho T HF dagger, you just need to take HF Ho T dagger, because this is going to be Ho dagger T H effective dagger, and you know that Ho is Hermitian, so this is going to be Ho T. Okay, so let's go for it. And if you calculate it, you find that this is going to give you, remember that this whole EE is real, right? We have seen that this is modulo square of that coefficient, just up here, hang on. here, you can see that Ho EE is real. So if you take the conjugate, it's going to be equal to Ho EE. Okay? So we're going then to write this as H bar omega plus H bar divided by 2 gamma square Ho EET and the projector onto the excited state, which is pretty much just getting the expression that we had calculated and computing then the adjoint. Brilliant. So we're getting there. And now we need just the last part, which is we need to calculate L hot C L dagger. So we need to calculate gamma GE, which is L. Just to remind you, this is L. And we plug in Ho, which is Ho EET EE plus Ho GGT GG. Then we have here gamma star EG, which is L dagger. Brilliant. So we have everything we need. We just need to compute. So when you apply this to this term, so let's call this 1 and let's call this 2. So we want to compute this. So we have, call this 1. So we have modulus gamma square already, G E E E E G, and here you have Rho E E T. So you can clearly see this is 1, this is 1, so that this first expression gives you then modulus square gamma G G Rho E E T. So you see you went 1 down because this is clearly now a projector onto the ground state, and you have some coupling here with the excited state in form of this coefficient. We want then to compute the equations for these coefficients. And for 2, which I'm going to call 2 is this guy, which we want to compute, we are going to have also modulus square gamma, Rho GGT, GE, which comes from L, and then you have G, G, E, G coming from L dagger. And these are autonomous states. So this is 0, and this inner product is also 0. Therefore, we know that this term is going to vanish. Therefore, we can conclude that L Rho T L dagger is modulus square gamma Rho EET GG. So it went down as we expected. We are saying that this operator is like making the system jump, and this is absolutely clear. And you transformed Rho so that Rho went from the excited state to the ground state, as you can see. This is like a transformation. So let's plug in into the master's equation, which was our first intention anyway, substituting into the master equation. We find that Rho dot T is equal to minus I H bar. This is what we want to do, right? Just recapping. Plus L rho T L diagram. But we need to take care a bit also of the left-hand side. So the left-hand side is this guy. If you differentiate, you get then rho dot EET EE plus rho dot GGT GG. You don't need to do anything about the states. They are eigenstates. They are not dependent on time. And we have then here minus I H bar. We can plug all these expressions which we obtained. H bar omega minus I gamma squared divided by 2 minus H bar omega plus I modulus gamma squared divided by 2. And this is all multiplying rho EET and this projector onto the excited state. So let's simplify this. We need to tidy this up. We can see these two cancel out. And we can also see that this cancels out. So we are still going to do some multiplications. And the second term is going to be plus gamma square rho GGT GG. Okay, so tidying this up, this bit, we find, okay, we multiply minus I with I here, you're going to have minus 2I. You're going to cancel out with the 2. So this is going to look as minus gamma square rho GGT, no, rho EET, sorry, EET, E, and actually here I made a mistake. He's also E, because we had already some non-vanishing matrix element, but we applied the ladder operator and we went down, or we applied the jump operator and we jumped down. Plus gamma square rho EET multiplied GG. Okay, so this is our result. And we have, in principle, what we need, because we have the evolution for the whole density operator, but we want to obtain equations of motion for the matrix elements. So we would like, let me write, aim, obtain evolution equations for the matrix elements. And what I'm going to do then, I'm going to multiply from the left with E and from the right with E, because here they are going to free this guy first. So I multiply from the left with the bra E, and from the right with the cat E. Okay, so let's do that. And if you do that, you see the following. you see that, let's get this left-hand side. No, copy. Maybe I can do some paste. Okay. So I have this left-hand side. Erase a bit, carried stuff it shouldn't. So I go with E and with E. So clearly, this is going to vanish because these two are orthogonal. This is going to vanish as well. So I end up with rho E T equals, and now for the right-hand side, this term is going to vanish because you're going to have then things coming from the left and from the right on this projector, which is clearly orthogonal. So you're going to have then that this is going to give you just the first term. So you have minus gamma squared 2. What is the rest? Let me copy this quick. Copy. So I'm gonna paste and get rid of this. Okay. Now we said we multiply from the left and from the right, right? So we're going to have here a bra coming from the left and a cat coming from the right. So you see clearly when you act upon these projectors, this is one, this is one. So this gives you rho E dot T is minus gamma square rho EET, which is a good result because this is a first order differential equation on rho EET. Now we want to release this order coefficient here. Remember that we have these two projectors, which is related to the probability of it being in the ground state. Okay, so we're going to do that. So if you want to get this guy, you have to multiply from the left with this bra G, and from the right with this cat G. Okay, so let's do that. And you do this on the right-hand side. On the left-hand side, I'm not going to repeat the operation here because it's pretty much the same modus operandi. And this is going to give me rho dot GGT gamma square modulus gamma square rho EET, which is also a first order differential equation, but you see that there is some coupling now of these constants. So I want to solve this, sorry, and I can integrate this first one. So copy, paste, and what I would like to do now is I would like to integrate this, and I also have the initial condition. My initial condition is rho EE0 is equal to 1 because we know the system is initially in the excited state. So to integrate this, we can write this as d rho EET dt equals minus gamma modulo square whole EET. We can then write this as GEET whole EET equals to minus gamma square dt. So I integrate this G whole EET whole EET minus gamma mod square E modulo square T plus constant. Therefore, I can say that whole EET is constant K, E minus gamma square T. So you see that you have some kind of exponential decay. And I know also that whole EE0 is equal to 1. Therefore, if I set time equals 0 here, I get that this is going to give me this constant, which means that whole EET is whole EE0, E minus gamma modulo square T. And this is very nice because this is showing you that this population is decaying as you expect with this rate modulo square of gamma. So let's plug this in. So here we can clearly see an exponential decay. Let me write it down because. So now we're going to calculate whole GG. Well, we have the expression, right? We know that whole GG dot T is whole GG dot T is gamma square whole EET, but this we have calculated already. Integrate. So we need to integrate this whole GGT dot dt, right? Or if you want, let me write this nicely. If you integrate, you have G whole GGT gamma square whole EE0 integral minus E gamma square T dt. Okay, so we have then whole GGT is gamma square whole EE0. Now this is going to give me 1 over modulo square of gamma. This is going to cancel out, and I keep this guy. Plus some arbitrary constant, we don't know. Now we know the initial condition, right? We know that initially whole GG is equal to 0 because everything is in the excited state. So we know this. So if you set time equals 0, we get that 0 is whole EE0 plus C, whereby this arbitrary constant has to be minus whole EE0, which then is going to give me that whole GGT is 1 minus E minus gamma squared T whole EE0. This is nice because you see we have now the expressions for all these coefficients and we have the state of the system. Then we can see how they are behaving. And this means always that the probability physically speaking, of measuring the state of the atom in the excited state, so that the atom is in the excited state, will decay exponentially with rate modulo square gamma. And this is cool because you can see that if you want to describe in principle spontaneous emission, this is much, much more complicated. You need to take into account many different things. For instance, second quantization of the field and these kinds of things. And here we have just assumed it is a Markovian. We have used a master equation for an open quantum system. And we brought these jump operators to make the system jump. And this is proportional to some decay rate. And we have calculated the whole thing. So you can see that these methods are ad hoc, but they are extremely powerful. And especially if what you're going to do with your system. For instance, to calculate gamma, we would need to do an ab initio computation, and this would be much more involved than we have done right now, but we were able to guess and to get, using our formalism, the overall behavior of the system. We know that the probability of the system being in the excited state is going to decay with this rate modulo square gamma. And this is very good. So this specific lecture is coming to an end, and I would like to make a series of remarks about phenomenological master equations. And in the example that we have just seen, with regard the spontaneous emission in a two-level atom and a jump operator, which is of this form. And this jump operator gives you a jump from the excited to the ground state with a single photon emission. You can do similar things for like a huge and wide range. And the strategy that you would pursue is pretty much the same or very similar. You identify the system Hamiltonian. You identify what your jump operator would be, depending on the dynamics that you want to consider due to the interaction with the environment. You can then use the opportunity and you can build a toolbox of jump operators corresponding to different types of system-environment interaction. And there you can use your creativity, you can use your common sense, and you have to see exactly what is happening to the system because of the environment. And then you can construct master equations to make them suit a particular problem. And phenomenological approaches, they are not rigorous, they are educated guesses. And one example that I mentioned is that you would need a much more involved first principles derivation to derive, for instance, the gamma that we have used in the spontaneous emission problem. But on the other hand, they are a very powerful method if you want to construct a quick model of an open system. And if this model, especially if you're clever and you know how to construct these things, they are going to match the evolution that is predicted either in the rigorous calculations or in the experiments. And this is a big, big, big plus. For instance, you can use jump operator and master equations if you're looking at a randomly varying magnetic field and spin. What you have is you have a spin that is going to interact with a magnetic field that is randomly varying. And because of these random variations, there is to be some classical randomness that is going to mix these spin states and is going to lead to some kind of dephasing. So you have to consider you have some kind of jump operator to be able to encompass that. And here you see you construct a jump operator considering spin projectors. And you're going to apply this somehow randomly. Also, if you have damped harmonic oscillators, for instance, we talked about spontaneous emission in the free space, and we mentioned, okay, sometimes we use cavities to enhance particular modes of radiation and capture photons if you wish, but you cannot capture in real life photons indefinitely in an optical cavity. Eventually, they are going to leak. And mathematically speaking, the process that is going on is similar to what you have with a damped harmonic oscillator. So you need to construct a jump operator that is going to account for this kind of photon annihilation. So you're going to have something that is proportional to the annihilation operator. So these things, they are very powerful because although not all systems are described considering Markovian evolution, and sometimes this will fail, obviously, it may still be in many, many circumstances a good approximation. And there are other applications. For instance, people are dealing with quantum information. They sometimes need to study noise, and this kind of formalism is very useful for that. If you're dealing with nanostructures as well, you're going to have a lot of noise and you're going to have multi-electron effects that you need to take into consideration somehow. And also if you have energy transfer in big molecules like biomolecules, this is something that is very useful to assess the role of the environment. And many, 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 many more systems. So this was just to give you an example. We're still going to see some examples in the synchronous lectures, but there are many, 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 many situations in which you will be able to apply this. And I would like to thank you also. Here I'm just putting some cats because of their role in quantum mechanics and because you wanted to see my other cat too. This is the last asynchronous lecture. So I would like to thank you all for your attention. And this has been a difficult time for everybody, me, you, and so on. And you have been a wonderful cohort. So I would like to say thank you. And I hope you enjoyed the lectures, and I hope that this is going to be as a scientist and that we are all going to learn something for our lives from here. So thank you very much, and have a wonderful time and all the best.